Hi everyone. So next topic which we need to study is your effect of temperature on the rate of reaction. Like if you increase the temperature, decrease the temperature, what is going to happen for the rate of reaction? Next topic is effect of temperature on rate of reaction. See, generally what happens in most reaction, whenever you increase the temperature, the probability of getting the reaction increases, right? So we can write in most reactions on increasing the temperature, rate also increases. On increasing the temperature, your rate is also increasing, right? So which definitely means your rate constant is also increasing. Correct, rate constant is also increasing. Because see, if rate is increasing, rate equals to your K concentration raised to the power n. So I am telling you, if temperature increases, rate increases. So if rate is increasing, definitely your K is also increasing, right? Now there are two things. One is your approx dependency on temperature, two things which you need to study. First thing is approx dependency on temperature, like approximately we'll see how much is temperature dependent, like how much is your rate dependent on temperature. Approx dependency on temperature. And second thing which we need to study, which will study, is your absolute dependency. This will give you the approx value and this will give you the absolute value. Okay, so let's shift to our first one, approx dependency of K on temperature. First thing is your approx dependency of K on temperature. See, generally it is seen on rise of temperature. Generally it is seen on rise of temperature by 10 degrees Celsius. Your K will approximately increase 2 to 3 times. This is usually seen that whenever your temperature, like if I have a temperature 10 degrees Celsius, my K value is 1. After I increase 20 degrees Celsius, my K will become 2 or 3, like it will double or triple. Okay. So for this they used a method. And what is this method called as? Temperature coefficient. This method is called as temperature coefficient. And what is it basically? Temperature coefficient is nothing but your ratio of two rate constant is your temperature coefficient. Ratio of two rate constants. So K1 by K2. Let's suppose my this particular, in the denominator was T degrees Celsius. After some time you increase the temperature, T degree plus 10 degrees Celsius. This is your what is called as temperature coefficient, and this value approximately comes out to be 223. Okay, we'll do some questions based on this. For example, let's say if I have 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius. What are you doing? You're increasing the temperature by 10 degrees Celsius every time, right? Here if you have 1 Kelvin, 1 K is the value, not Kelvin, sorry, K. Here your temperature coefficient might be 3. Here it will be 6, here it will be 9 and so on, right? We'll do one question based on this approx dependency of K on temperature. The question tells you, for a particular reaction, your temperature coefficient is 2. For your particular reaction, temperature coefficient is 2. if ROR at 20 degrees Celsius is given to you as X, what you need to do, find the rate at 20 degrees Celsius, 80 degrees Celsius. So what have they given? For a particular reaction, temperature coefficient is 2, like K upon K, that is temperature coefficient, K1, K2 here, right? ROR at 20 degrees Celsius means is X. So if this is X, means at 30 degrees Celsius, it's increasing 2 times, right? So 30 degrees Celsius will be 2x, at 40 degrees Celsius will be 3x, 50 degrees, 4x, 50, 60, 70, 80. So what's going to happen? 4, 5, like it's increasing 2 times, right? 2 2s are 4. 4 into 2, 4 into 2 is 8. 8 into 2, 16. 16 into 2, 32. 32 into 2, 64x. So our rate constant will be 64x. So this was the approx dependency of K on temperature, right? Now we'll see accurate dependency. The second kind of dependency is accurate dependency of your K on temperature. First you learn the formula, which from where you need to start. The formula is K is equal to AE minus of EA by RT. Now what are all the terms? K is equals to AE minus of EA by RT. K is definitely your rate constant. A is your frequency factor. Frequency factor. This is also called as Arrhenius factor. Arrhenius factor, also called as pre-exponential factor. Pre-exponential factor. What is E? E is your exponential constant. E is your exponential constant. R is your universal gas constant. Universal gas constant. T is your temperature, and what is left? E is your activation energy. And this formula has particularly come from your collision theory. K is equals to AE minus of A by RT. This formula has come out from your collision theory. Now, what is collision theory? We'll study next. Collision theory. We studied in a previous lesson also what is collision. Like reactants collide to give you the product, right? But some collisions are only effective and give you the product, whereas some collisions are not effective and they don't give you the product. Those are non-effective collision. Okay, so for your effective collision, what matters is your effective collision. For effective collision, the first thing which matters is your orientation barrier. The first thing which matters is your orientation barrier. What does your orientation barrier tells you? Molecules should be properly oriented so that they can collide to each other. And what is the proper orientation here? Head-on-head orientation. If some molecule is like this, they cannot collide easily, right? If some molecule is like this, cannot collide properly and give you the product. So first thing is there should be head-on collision. Like suppose there is A molecule, B molecule. both heads are colliding together to give you the product. This is my product, suppose. So there should be head on collision. Head on collision. If your molecule is lying simply like, like this or this, not effective, not effective. If it's like this or this, not effective. So first thing in collision theory is your molecule should have proper orientation. Second thing which is important is energy barrier. Second thing which is important is your energy barrier. So here if I tell you this is my energy on the y-axis, here it's my reaction coordinate in my x-axis. This is my reactant and this is my product. This is my total energy, and from here to here is my energy of activation. This energy is 50 joules. Okay, here the maximum energy is 50 joules what the molecules reached. Now suppose the molecules were already having 10 joules of energy. How much more joules of energy is needed more to reach till here? 40, right? So this 40 will be energy of activation. Product energy can be anywhere. It can be here also. It can be below also. So if it is below, it means energy is released, right? Energy has come down. Energy is released. So if it's below, it's exo. If it's above, it means it is endo. Okay, now how do we come from conclude the formula from this energy barrier? Let us see a graph. This is my fraction of molecules, and here I have kinetic energy. This is my 25 joules. Now can you see maximum molecules are at 25 joules? Fraction of molecules, how many fractions? Say 0.5. Half of the molecules are having this kinetic energy. Rest half may be having 0.2 here. 0.2 molecules might be having this energy. 0.1 molecules can be having this particular energy. Okay, fraction of molecule is 0.5. Now from graph you can see maximum molecules are having what energy? 25 joules of energy, right? Fraction of molecules. Now how do we arrive at the formula? We'll write fraction of molecules which cross the energy barrier, which is trying to cross this energy barrier. Fraction of molecules which which cross the energy barrier fraction of molecule which cross the energy barrier at temperature T. How much will it be? T is it's through a formula. T is equals to E minus of EA by RT. So kind of rate is directly proportional to E minus of EA by RT. If I want to put a constant, what will be my constant be? Like I can write K also is directly proportional to E minus of EA by RT. K is equals to A into E minus of EA by RT. This is how I got my formula. Now what will I do? I'll take natural log on both sides. Ln k is equals to ln AE minus of EA by RT. So what will it come out to be? Ln k equals to ln A, I can write it down, plus ln E minus of EA by RT. Now ln k equals to ln A, I can write it like this, minus of EA by RT ln E, right? Now we know log base anything, log base k will, ln k will be equal to log base ek. So I can write it down as log base, like this particular thing, I can write it down as log base e raised to the power e. So this is practically equal to 1. So what will I get? Ln k equals to ln A minus of EA by RT. I can write it as log also, right? Log base E k equals to log base E A minus of EA by RT. So this is my second formula. First formula was this, k is equals to AE minus of EA by RT. The second formula is log base EK is equals to log base A minus of EA by RT. Now how will you draw the graph of this? What formula did we get? Log base EK equals to log base EA minus of EA by RT. So if I just substitute and write it like this, log base k is equals to minus of EA by RT plus ln of A. Like 1 by t I can write like this, correct? So this is in the formula, y is equals to mx plus c. So if I want to draw a graph, what will be on my y axis? Ln k. My x axis will contain 1 by t. What is happening? Like the constant, it's decreasing, right? It will be like this. This will be ln A and slope will be equal to minus of EA by R. Okay, now we know ln EK equals to, like this also I can write it down as 2.303 log base 10. In log base 10, what can I write? Log base 10k, correct? Can write log base e raised to the exponential k. I can write it down as 2.303 log base 10k. So what will I get? Two 2.303 log base 10k will be equal to your 2.303 log base 10k log base 10a minus of EA by RT. So just divide this full equation by 2.303. What will I get? Log base 10k equals to your log base 10a minus of EA by RT, and this is your formula which is used the maximum number of times. So this will be y is equals to, this will be c, this will be x, and this will be m. So how will your graph look like? Like this. Okay, same thing like this. So these are the three formulas which you need to remember. What was the first formula? Don't learn the second one not that important. Okay, so let us do some questions based on these terms. You have been given a graph log base 10k 1 by t, and this is your decreasing this thing 60 degree. Okay, what are they telling is find EE. Now how did our formula look like? Our formula looks something like this, right? Log base 10k equals to log base 10a minus of EA by RT. What do we don't know? Like this was our slope, right? Slope is equals to EA by R. So can I write my slope is equals to minus of EA by R? which is equal to your tan theta, right? What will be your theta? As I told you, always the right side of the left hand. So this is your theta. Theta is your 120 degree. So tan 120 degree equals to your minus of EA by R. EA by R, or we can write it down as 2.303 R. If you're writing in log, it is 2.303 R, right? 2.303 R. So what will be EA? Tan 120 is root 3. You can solve the rest. Root 3 into 2.303 into your R. 303 into your R. Okay. The second question. Second question is telling us, for your nth order reaction, frequency factor, what does your frequency factor means here? A, right? Frequency factor is 100 and activation energy is your 19137 joules per mole. What you need to find? The rate constant at find the rate constant at 727 degrees Celsius. Now if you want to convert the 727 degrees Celsius into Kelvin, what will it come? 1000 Kelvin, right? So we'll apply the formula log base 10K equal to log base 10A minus of EA by 2.303 RT. What do you need to find? Rate constant K you need to find, right? So substitute all the values. Log base 10 A. What is your A? Frequency factor is 100 minus of 19137 upon 2.303 into R is your 8.314 into your temperature is 1000. You can write this as log base 10 to the power 10 to the power square minus minus 19137 divided by 2.303 into 8.314 into 1000. When you solve this particular thing, it will come out approximately 1. So 2 minus 1, which is equal to your 1. So log base 10K is equal to 1. So what is the anti-log? 10 to the power 1. So K is your 10 to the power 1. Okay. Next question. Next question. Next question is telling us, for a first order reaction, it's already given, okay? It's a first order reaction. Rate constant is given by this. Log base EK minus is equal to 10 minus 12 into 10 to the power 4. Okay, 1.2 into 10 to the power 4. It's 1.2, okay? Divided by T. So what you need to find first? Find the temperature. You need to find the temperature at which half-life is 70 minutes. Half-life is 70 minutes. Now, since this is already given, okay, this is a first order reaction. So, what is T half? T half is 0.693 by K. And what will be K here? T half is already given, 70 minutes, 0.693 by 70. So this will be approximately, like if I want to write approx, 0.7 by 0.70 by 70. So this will come out to be approximately 10 to the power minus 2, right? 10 to the power minus 2. Now just substitute your T here from second to first. So log base E 10k equals to, this is 10, okay, 10 minus 1.2 into 10 to the power 4 divided by 10 to the power minus 2. Sorry, this is your 10 to the power minus 2, right? This is your temperature. So what will it be? Minus 2 equal to 10 minus 1.2 into 10 to the power 4 divided by temperature. Then your temperature will come out to be approximately, it will be 1000 Kelvin. Okay, easy. Then second part is telling you what is the value of A. What is the value of A? Now, how will you find this particular thing? We know log base EK equals to log base EA minus of EA by RT. Okay. Now, log base K was already given to you, right? EA by RT is also given. Everything is given to us. This we know, this we know. First order reaction log base 10. Like if I want to do log base 10k, this is equal to your 10 to the power minus 2. Log base EA we don't know. Minus of EA by RT. So R we already know now. Temperature we already know. EA is already here. So with this you need to find the A. So automatically by substituting all the values you will be getting the A. Next topic which you have to do is ratio of two rate constant. Very easy. Ratio of two rate constant at your two different temperatures. Nothing you need to do, just apply the formulas. Log base 10 K1 equals to log base 10A minus of EA by 2.303. Now it's different temperature, right? RT1. This is my first equation. What will be second? Log base 10 K2 equal to log base 10A minus of EA by 2.303 RT2. What do you need to do? You need to do just do 2 minus 1. What will it come out to be? Log base 10 K2 by K1, this and this will get cancelled, equal to EA upon 2.303. R became common. If I'm not taking minus inside, okay, 1 minus T1 minus of 1 upon T2. This is the equation. Or you can just take the LCM also, T1 by T2, T2 minus T1. Easy. One equation will do based on this ratio of two rate constant. The question is telling us at 27 degrees Celsius, your K1 is 1.5 into 10 to the power 4. Second inverse. And at your 127 degrees Celsius, your K2 is 1.5 into 10 to the power 5. What do you need to find? Find the activation energy. So just substitute it in the previous formula. K2 by K1, 1.5 into 10 to the power 5 divided by 1.5 into 10 to the power 4 equals to your activation energy we need to find 2.303 into R, 8.314, 1 upon T2, or we can just do T2 minus T1. So just convert it into your Celsius. You will get 400 minus 300 divided by 400 into 300. Just solve it and you will get the answer. So basically 3 formulas we have seen, right? Revision of temperature we'll just do. What did we see? For first we saw how do we predict the variable temperature, like a rough idea of temperature, that with every 10-degree rise in temperature your K is increasing 1 or 2 times, right? Then absolute, we came out with the formula K is equals to AE minus of EA by RT. Second formula which we came out was log base log base 10 raised to the power K equals to log base 10 A minus of EA by RT, 2.303 RT. And third one was the ratio log base 10 K2 by K1 equal to EA upon 2.303 R in denominator T2 T1 T2 minus T1. These are the 3 formulas which you need to thoroughly remember. K is equals to AE minus of EA by RT, log base 10 K is equals to log base 10 A minus of EA by 2.303 RT, log base 10 K2 by K1 equal to EA upon 2.303 R and T2 T1 minus T2 minus T1 upon T1 by T2. Okay, there are some exceptions, wherever you increase the temperature there is an exception, many exceptions, where your rate constant may or may not increase. First is your bacterial decomposition. So you must have heard of it that bacteria work at a particular temperature only. More than it, less than it, they won't work. They need an optimum condition, right? They need an optimum condition. So in this case, it doesn't work on medium temperatures and all. Second thing is oxidation of NO. So we have the reaction as 2NO plus O2 is giving me 2NO2. Now once we see rate and temperature, its rate is actually decreasing. Okay, negative temperature coefficient we are getting. Negative temperature coefficient we don't usually get it, right? Because it's showing us that as temperature is increasing, your rate is decreasing. So oxidation of NO is an example. Next is explosion. So you must have seen rate increases suddenly, right? It doesn't happen gradually. So these are the 3 examples of your exceptions. Okay, so I hope everything is clear. Practice more questions based on this topic. Thank you so much.